Hello AP Chemistry. This is the video that goes along with Lab 9, Experiment 22. You will find the handout, the full-length handout in OneNote. You will also find a shorter handout that has all the fillable forms for both the pre-lab and the lab report. That's the handout that I'm going to be grading. So everything that I talked to you about today, you should be filling out this information in the on those handouts in OneNote so you can turn in the lab digitally to me. All right, so this experiment is called the colorimetric determination of an equilibrium constant in aqueous solution. So our goal for this lab is to determine what this is. Okay, this is the equilibrium constant. This is the experiment that we're doing. It's kind of a weird looking experiment, right? These in red are the actual chemicals we're using: iron chloride and sodium thiocyanate. That's what this is called. Right, but we've removed the spectators and put the net ionic equation here with our iron 3 ions, our thiocyanate ions, and then this complex here, which is basically iron thiocyanate. Okay, and it's red in color. This is clear and this is yellow. So I'm going to perform the reaction for you real quick. I've got my two reactants here. I've got my iron and my thiocyanate. I'm going to first put a few drops of my thiocyanate into a test tube. All right, 1, 2. And then I'm going to take my iron and put just a single drop in here, and let's watch and see what happens. All right, it's good. You can see that just that single drop is enough to make almost a red solution there. All right, we can push it further to equilibrium by putting in a little bit more red, like this. All right, there we go. We can see that red solution get made in here like this. Put even maybe a little bit more in here to push it further and further to the right on the equation. What do I mean by that? All right, I'm saying that as I add more of this, right, Le Chatelier's principle says that as I add more of this, the reaction pushes itself to the right, and if the solution becomes more red, you can see that happening right here, okay, as I make the red solution from these two solutions. Now, if I could somehow push the reaction back the other way, I could decolor the solution. There's a lot of ways we could do that. We could somehow remove this ion. We could somehow add more of this ion. That could push it back, but then we get more red here. What I'm actually going to do is I'm going to precipitate the iron 3 ions by adding some hydroxide. The compound that I'm going to make when I do this is iron 3 hydroxide like this, and this is a solid compound, right? And so I'm going to be removing this compound, and Le Chatelier's principle says that if you remove a compound, you shift equilibrium to fill the other way. So when I remove this compound, we should shift this way, and we should remove the red color and make it colorless again. Let's see if we can do that. Here we got this. We got our red solution here. I'm going to go ahead and put a few drops. This in here, right? And there you go. We can see the red disappear there as we shift equilibrium away from the red chemical. Okay, so that's a little demonstration on the introduction to this chemical reaction that we're going to be studying in this lab. This is what we're looking for in the lab. So what we need to know eventually are the equilibrium concentrations of these 3 chemicals so that we can solve for KEQ. That's the goal. And prepare our 6 solutions for our calibration curve. If you remember from our previous labs, a calibration curve is something that we can use to change absorbance to concentration, right? And this is the chemical that we'll be most interested in, this red compound that absorbs 430 nanometer light. I'm going to create some solutions that I know the concentration of, right? But I don't actually have this chemical. That's the trick here. Okay, so when I finish making the solutions, I'm going to come back and I'm going to tell you how we actually know the concentration of this compound in all these solutions. So let's just go ahead and make them first. All right, this is our formula here. I've got 10 milliliters of 0.2 molar iron 3 in each of these graduated cylinders. Right? That is very, very concentrated. It is 1,000 times more concentrated. Oh, not 1,000. It is 100 times, sorry, more concentrated than the thiocyanate ion, which is only 0.002 molar. okay? And I'm gonna put between 0 and 5 molar in each of these, okay? So let's go ahead and get started with that. This is my 0.002 molar thiocyanate chemical right here. I'm gonna take my graduated pipette. I'm gonna put nothing in the first one, that's 0. Solution 1. In solution 2, I'm gonna put... So if you can see, of course, it gets darker as we go across, right? Because I have 0 thiocyanate, 1 milliliter, 2 milliliters, 3 milliliters, 4 milliliters, 5 milliliters, okay? And now the next thing we're gonna do is we're going to fill it up to a total volume of exactly 50. I'm gonna roughly fill it by just adding, or just pouring straight from this. I'm gonna get each one of these things close, right? And then after we get each one close, I'll come and top it off and get it at exactly 50 when we're all done. These are our 6 solutions here that we just made. You can see that they get darker as we added the thiocyanate ion. And what we're going to talk about now is how we can actually calculate the concentration of our chemical of interest here, this iron thiocyanate, right? It's going to absorb 430 nanometer light, so this is the chemical we're most interested in. All right, so how are we actually going to determine its concentration? It's a little tricky. All right, so the way it works is Le Chatelier's principle says that because this chemical right here is 0.02, which is almost 100 times more concentrated than our thiocyanate, that it pushes on equilibrium here so much that 100% of this chemical becomes this chemical right here. So when you use this information to determine the number of moles of thiocyanate, all of those moles become moles of iron thiocyanate, our red compound. You can then take those moles and divide it by our total volume of solution to come up with our concentration of our iron thiocyanate, which we will compare to our absorption that we're going to measure. Absorption of all 6 of my solutions, 1, 2, 3, 4, 5, 6, with my colorimeter. It's been calibrated with distilled water and set to 430 nanometers. All right, so here's solution 1 in this cuvette. We're going to place it inside, close the lid, and see the absorption here of about 0.024. So you should record that to make your calibration curve. That's our first solution there. I'm going to empty this out. I'm going to give it a quick little rinse with distilled water. Like this. All right, and then I'm going to add solution number 2. Same cuvette. You can see it's a little darker. Put that in here like this. We see that this one's got a concentration of 0.0, or looks like just about 0.1, okay? 0.1 for solution number 2. All right, on to solution number 3. Quick rinse. Here goes solution number 4. Wipe off the sides real quick. You see we got about 0.152 or 0.153. Hopefully you can see that. 0.153 for solution number 3. Okay. Moving on, solution number 4. Okay, so here goes solution number, oh, sorry, that was solution number 3. Here goes solution number 4. We get 0.254. 0.254 for this, or 0.255, sure. Okay, moving on. This is solution number 5. absorption of 0.367 or 0.368. 0.368 for that one. Okay. Awesome. And last but not least, solution number 6 should hopefully give us the largest absorption here. It's the darkest. And there we go. 0.436. This is the last step of the lab here, where I have made the final 6 solutions, 1, 2, 3, 4, 5, and 6. They all have 5 milliliters of our diluted iron solution here. The concentration of the two is now the same, so we're not pushing equilibrium all the way to completion. All right, and they have 0, 1, 2, 3, 4, and 5 milliliters of our thiocyanate here. And they are filled to a total volume of 10 with the nitric acid. You can find this in part B on the handouts. All right, so now it's time to take the actual concentration, or the actual absorbance of each of these. I'm going to take my water here. All right, we're going to do this real quick. Get the absorption measurement of each one of these things. All right. So here goes the first one. It shouldn't be very much. In fact, it is a whopping 0 because there's nothing in here. There's no equilibrium because we did not put any thiocyanate in there. Okay, next one. The absorbance of this one is 0.131. That's for solution 2. Hopefully you're recording this on your sheet. Here goes solution number 3. Solution number 3 is 0.263. 0.263. Solution number 4. Solution number 4 is 0.395 is the absorption of solution number 4. This one's solution number 5. Solution number 5 here, it has an absorption of 0.482, 0.482, that's solution number 5. And last but not least, solution number 6. All right, solution number 6. 0.354. So solution number 6 has actually gone down again. You should make note of that. Okay, so those are the absorptions from all 6 of those solutions. You should be able to use your calibration curve to determine the equilibrium concentration of this and plug it in right here on our ice chart. You should have one of these ice charts for every single one of these test tubes because there are different concentrations here for each one. All right, now from that, we should be able to go from 0 and find out what x is, right? Hint, it's going to be plus this. And over here, it's going to be minus whatever you get here for this and this. Then all we need to know is our initial concentration of these 2 chemicals. And what you need to do is calculate the initial moles of this that you use, divide it by our final volume. an initial moles of this, divide that by its final volume, and you can plug in those numbers here and here, subtract by x, and we should be able to get our final equilibrium concentrations here. These ones should come from filling in the ice chart, and this one here comes from our calibration curve. Once you have all of these, you plug it into the equilibrium expression, and you're going to solve for k. You're going to solve for k 5 times. We can't actually solve for it from here because this number is going to be 0, right? We don't actually have an equilibrium in that case, but in solutions 2 through 6, you should be able to come up with equilibrium concentrations and come up with your equilibrium constant. Good luck, and let me know if you have any questions.